Hi again. Today I want to take a look at something called the ideal gas law. First off, let's look at the properties of what is considered an ideal gas. First off, an ideal gas, the particles act as single point masses, meaning the particles themselves are extremely small and take up almost no space. They also exert no attractive forces between each other because the distances are so far apart and the forces between them so weak. The closest thing we have in terms of a gas that behaves like this might be something like helium or hydrogen gas, which would have only very small van der Waals forces between them, and the particles themselves would be extremely small. Particles of an ideal gas follow Boyle's law, a perfect inverse relationship between pressure and volume. And similarly, they also follow Charles' law, again a proportional relationship between volume and temperature. But in reality, particles do take up space. They do have volume. When you move to gases, say such as chlorine gas, they become quite large, or even water vapor molecules, they can have considerable attractive forces between them. So as a result, when the volume gets very, very small, these particular factors come into play. Particle volume starts to become quite significant, and the attractive forces become quite large. As a result, these curves don't quite follow the shape that's shown here. In the case of a real gas, when our volumes get very, very small, the particles almost touch each other, and you can't get them any closer together. The volume reaches a limit, and it can no longer become any smaller. And similarly, when particles become very cold and slow down, they often change states, turning into, say, liquids or solids. And once again, the particles can't get any closer together. So, when we have conditions of very low temperature and very high pressure, behavior between ideal and real gases differs significantly. Anyway, we're going to focus on the behavior of ideal gases. Again, our relationships, Boyle's law says that our pressure is inversely related to our volume. It would also be equivalent to say that the volume is inversely proportional to the pressure. Charles' law relates our temperature and our volume. And finally, from Avogadro's law, the volume of a gas is proportional to the number of moles of particles present. I want to combine these three, and as a result I can say the volume is inversely proportional to the pressure times the temperature times the number of moles. If I wish to replace the proportionality sign, I can do that by replacing it with an equal and introducing a constant, so the volume now would equal R NT over P. This is often rewritten as PV equals nRT, and this is the equation that's available in your IB data booklet. Now a little bit about R. R is called the universal gas constant, and its value typically is 8.31 joules per Kelvin per mole, also in your IB data booklet. I want to look a little bit more carefully at the units here of R. As mentioned, it has the units of 8.31 joules per Kelvin per mole. Now the joule, for physicists out there, a joule is a Newton, a unit of force, times a meter. So I'm going to replace the joule with a Newton meter. I'm now going to multiply top and bottom by the same thing, by meters squared. That now gives me the following expression. A Newton over a meter squared, that's the unit of the Pascal. And meters cubed, that's a unit of volume. So to use this particular equation, PV equals nRT, the units are very specific. The number of moles must be used, the temperature must be in Kelvin, the pressure must be expressed in pascals, and V in cubic meters, or meters cubed. But there is an alternative as well. If I take that expression and again I multiply top and bottom by 1,000, or a factor of 1, I get the following. 1,000 newtons per meter squared is the unit of the kilopascal, and meters cubed divided by 1,000 gives us decimeters cubed, or liters. So this gives us a second set of units that could be used. Moles, Kelvin, pressure expressed in kilopascals, and decimeters cubed, or liters, as the volume of our gas. So don't mix these two units. They have to be either units 1 or units 2. Let's solve a particular problem here. Determine the volume of 1 mole of a gas at STP, standard temperature and pressure. I'll list my given information. 1 mole of gas, I want to know its volume, temperature 0 degrees Celsius and 100 kilopascals. First thing I notice is I have to get that temperature in Kelvin to use the the ideal gas law. And the second thing I'm going to note is the fact that the unit of kilopascals is specified here, so I know that that means my volume will be in liters, or decimeters cubed. So, PV equals nRT, rearranged to get the volume of 1 mole on one side of the equation, and substituting in my units and solving. So, 22.7 decimeters cubed. This is called the molar volume of a gas at STP, and it's also available in your IB data booklet. No matter what the gas, 1 mole of that gas at STP will always occupy 22.7 decimeters cubed. Let's look at a problem involving the density of a gas. I want to determine the density in grams per cubic meter of carbon dioxide gas at 20 degrees Celsius and 101.3 kilopascals. I'm going to list my given information. Since I know the gas is carbon dioxide, I've incorporated its molar mass here. I would like to know its density, temperature 20, and 101 kilopascals. Again, the temperature must be expressed in Kelvin. And I notice here that they require my density in units of volume that are cubic meters. For that reason, I'm going to change my units of pressure into pascals by replacing the kilo with times 10 to the 3. So 101.3 times 10 to the 3 pascals will be my pressure. Now there's the universal gas, I should say the ideal gas law, PV equals nRT. Now I'm going to replace the number of moles with mass over molar mass, small m over capital M. And I'm going to further rearrange the equation to get density by itself on one side, density being mass over volume. And you can see that in the final expression. So pressure times the molar mass divided by the universal gas constant in T will give you the density of my gas. Substituting in the values and solving, I get 1.83 times 10 to the 3 grams per cubic meter. Now a little note here about significant digits. You can see here my molar mass has 3, my temperature has 2 significant digits when I look at it in Celsius, yet 3 when I go to 293, and the pressure has 4. Now I'm going to look a little bit more closely at the temperature. Recall that when you add 2 numbers together, it is not the significant digits that matter, but the decimal place. So when 20 is added to 273, that value is good to the ones column. 293 then is good all the way to the ones column, or has 3 significant digits. That's the least significant of all of my data, so I round my final answer off to 3 significant digits. Questions are always welcome. Thanks for watching.